This is Lecture 2, Collecting and Measuring Data. By the end of this lecture, you should be able to understand how researchers measure concepts in quantitative political science research, classify and describe a variable based on its unit of analysis, evaluate whether a variable measures a concept in a valid and reliable manner, compare variables that measure the same concept in different ways, write a variable's conceptual definition, write a variable's operational definition, and read and comprehend the information in an SPSS dataset. In the previous lecture, I briefly reviewed the basic steps in conducting a statistical analysis of political science research. Before I go into more detail how to conduct statistical research in political science, first I need to teach you how to measure concepts and variables. If you do not know how to measure concepts and variables, you will not be able to conduct any statistical analyses. Hence, this lecture is all about collecting and measuring data. Political scientists study concepts such as liberalism and conservatism, and equality and inequality. These concepts are not tangible. You cannot touch them or hold them in your hand. You cannot see them. You cannot hear them. Nevertheless, we know these concepts exist. They exist as mental constructs. Since these concepts are mostly mental constructs, we have to make sure we have a good definition of what they are if we want to measure them and collect data on them. For example, we may have a general idea of what war looks like. Two states may use physical force against each other. They may destroy each other's property, and there may be battle deaths. However, not all conflicts between states are wars. Sometimes two states will have a single battle in a single day and the conflict will end. Is a one-day conflict a war? Not really. So how do political scientists distinguish between wars and short-term conflicts? One way to do it is to use battle deaths as a criterion. The correlates war dataset classifies any conflict between states with 1,000 or more battle deaths as a war. In this lecture, I will show you how to define concepts so they are measurable. In order to measure a concept, we need to develop a more concrete idea about what the concept means. The first step in this process is developing a conceptual definition of the concept. A conceptual definition is a concrete and well-specified definition of a variable. It tells us what we have to observe in the real world to measure our variable. A conceptual definition first includes the unit of analysis. The unit of analysis tells us who the concept applies to. Is it individuals, is it parties, is it countries, or is it pairs of countries? It also tells us where they exist and when they exist. The conceptual definition also identifies a concept's measurable properties that we can observe in the real world. Here is an example of a conceptual definition for ideology. Individuals who are liberal believe that it is appropriate for the government to redistribute resources from the wealthiest citizens to the poorest citizens. Individuals who are conservative believe that it is inappropriate for the government to redistribute resources from the wealthiest citizens to the poorest citizens. Note that individuals is the unit of analysis as it tells us what the concept applies to. Individuals have ideological beliefs. Note that the following information tells us what the variable's measurable properties are. We know an individual is liberal if they believe that it is appropriate for the government to redistribute resources from the wealthiest citizens to the poorest citizens. And we know an individual is conservative if they believe that it is inappropriate for the government to redistribute resources from the wealthiest citizens to the poorest citizens. In the next slides, I will show you how to develop a conceptual definition. As an example, we are going to develop a conceptual definition of democracy. The first step in creating a conceptual definition of a variable is to identify the variable's unit of analysis. Recall that the unit of analysis tells us who the concept applies to, who or what they are, and when they exist. The who of a unit of analysis could include a lot of different types of individuals. It could be individuals such as survey respondents, students, candidates, legislators, or judges. The what of a unit of analysis could include a lot of different types of entities. It could be political parties, countries, or international organizations. The when of a unit of analysis tells us when the who or what existed in time. It could be days, months, years, or even centuries. Here is a unit of analysis for a level of democracy variable. Since democracy applies to countries, countries is the unit of analysis. And I indicate what year I am examining those countries in, 2017. The next step in developing a conceptual definition is identifying the concept's measurable properties. These are properties that we can observe in the real world. For example, if we were writing a conceptual definition of democracy, the measurable properties of democracy can include whether a country has elections, whether leaders of a country are held accountable for their actions, and whether the country has a highly developed economy. Those are all potential properties of democracy that we can actually observe in the real world. After we identify the concept's measurable properties, we have to modify our list just to make sure that we are only including relevant and measurable criteria in the list. For example, in our previous list, elections and accountability were good measurable properties because all democracies should have elections with elected officials who are held accountable for their actions. However, we should leave out the economic development property. Economic development is not an inherent property of democracy. As long as a country has elections and leaders are held accountable for their actions, it is a democracy. Its economy does not need to be developed. A country could be a poor democracy. After we modify our list of measurable properties, we write down our conceptual definition. You can use the following template to write down a conceptual definition. The concept of X is defined as the extent to which subjects exhibit the characteristic of Z. So using our democracy example, we would write, the concept of democracy is defined as the extent to which an individual country holds regular elections and holds leaders accountable for their actions. Democracy is our concept. An individual country in 2017 is the unit of analysis, and holds elections and holds leaders accountable for their actions is the measurable properties. Next, we will discuss how to develop an operational definition. Recall that an operational definition tells us specifically how the concept is measured. The operational definition includes the unit of analysis, the values the variable takes, what those values mean, what we have to observe in the real world to determine the value each observation takes, and the source of the data. Here is an example of an operational definition for an ideology variable. The unit of analysis is the individual in 2016. The values the variable takes are 0 or 1. A 0 means liberal and a 1 means conservative. The specific criteria for coding it is as follows. A person who says they believe that it is appropriate for the government to redistribute resources from the wealthy citizens to the poor citizens is coded as liberal. A person who says they believe that it is not appropriate for the government to redistribute resources from the wealthiest citizens to the poorest citizens is coded as conservative. And the source of the data is the American National Election Survey. The first step in writing an operational definition of a variable is identifying the variable's unit of analysis. Recall that the unit of analysis tells us who the variable applies to, who or what and when they existed. The unit of analysis should be the same unit of analysis from the conceptual definition. Using our democracy variable as an example, our unit of analysis from the conceptual definition was countries in the year 2017. The next step in establishing this is establishing the specific observable criteria for your variable. For example, if we were measuring democracy and we wanted to measure elections, we would specifically examine whether a country has free and fair elections, where every adult can participate and the rules do not favor one party over another. In addition, we will want to make sure leaders are held accountable. One observable and measurable way leaders are held accountable is having to face re-election at fixed intervals. The next step in creating an operational definition is identifying the values your variable will take and what those values mean. For example, with our democracy variable, we can make a rule that when we identify a country as democratic, meaning it has free and fair elections and leaders face re-election at fixed intervals, we can give it a value of 1, and all other countries will receive a value of 0. The last step in creating an operational definition is identifying your data sources. Your data sources tell you whether your subjects meet the specific observable criteria in your variable. We can either use data we collected, which is called primary data, or use data that other people have collected, which is called secondary data. If we wanted to collect primary data, we could use information from news reports, government documents, surveys, or experiments. There are a lot of places we can collect data from. Of course, there are a ton of political science-related data sets out there that other scholars have already created, so often it's just easier to use data other people have created instead of creating our own. So in our previous example, we stated that we would classify a country as democratic if it had free and fair elections, where every adult could participate and the rules do not favor one party over the other. In addition, leaders in a country have to face re-election at fixed intervals. We could use the CIA World Factbook as a data source in this case to determine if different countries throughout the world meet those two criteria. The variable we created would be a primary source as we collected it. And here is the operational definition of democracy in full. After we develop our operational definition, we can then enter the data into a statistical software program. In this class, we will be using a program called SPSS to analyze our data. In SPSS, in the Data View tab, you can enter in the data for your data set. The first thing you should know is that the column headings should identify the variable names. Typically, the first couple of variables in your dataset should identify your dataset's unit of analysis. So in this dataset, the subjects of the dataset are countries, and the time is the year 2017. So we know the unit of analysis for this dataset is countries in the year 2017. The subsequent column headings should be the names of the variables. So the first variable in this data set, substantive variable, is GDP per capita. Next, the rows are where you enter in the data for the individual observations. So for observation 5, the country is Luxembourg, the year is 2017, and the value for GDP per capita is $109,100. Now, for the most part in class, you will not be entering in your own data for your assignments. Instead, you will be working with data sets other people have created. Hence, you will have to know how to read data sets when you use them. So if you need to figure out how to read a data set and figure out its unit of analysis, you should use these basic rules. However, it is important to note that it might not be possible to follow all those rules when creating a data set, and so the structure of data sets vary. For example, it is possible that while the type of subjects in a data set should remain constant, the time in which data are collected for those subjects might vary. For example, if we were to collect data on countries for GDP per capita and for the unemployment rate in those countries, we might not be able to collect data for both of those variables for the same year. While the subjects of the unit of analysis should be constant in the data set, but the timeline might not be, that means the unit of analysis for each variable in the data set might not be exactly the same. This is not an issue if you do not want the time frames to be the same, or if the data are from within a reasonable time frame, such as within 5 or 10 years of each other. Since there is variation in the structure of data sets, this makes it a bit difficult to figure out what a data set or a variable in a data set's unit of analysis is. As such, you can use these tips to help you figure it out. Sometimes the unit of analysis is implied from the data set name and not included as a variable in the data set. Sometimes the subjects, such as the who or the what, of the unit of analysis is included as a variable in the data set, but not the time frame. The data set name might have the time frame, or the names of the variables might have the time frame. Sometimes the time frame of the unit of analysis is included as a variable in the data set, but not the subject, the who or what. The data set name should indicate what the subjects are. Here's an example of a data set where it's not clear exactly what the specific unit of analysis is for the data set. The subjects of the unit of analysis is not included as a variable name, but the name of the data set is states, and all the data is from the United States, so it is acceptable to assume that the subject of the unit of analysis is the U.S. states. Also, there is no variable in the data set with the time frame in it. Instead, the variable names seem to have the years listed in them. So for the Obama 2012 variable, which measures Obama's vote share in a state, it is safe to assume that this data was from the 2012 election. Hence, the unit of analysis for this particular variable in this data set is the U.S. states in 2012. After we write our conceptual definitions and collect our data, we can classify what kind of data set we have. This classification will be based on your unit of analysis. Recall that the unit of analysis tells you who or what the variable applies to and when the who or what existed. Based on the unit of analysis, you can classify your data set as either a case study, cross-sectional time series, or cross-sectional time series. This chart here can help you determine what kind of variable you have. If your variable only applies to one subject and you only have a few observations for that subject, then you have a case study. An example of this would be studying democracy in the United States in 2017. There would only be one subject, the U.S., with a couple of observations in 2017. If your variable only applies to one subject, but you have multiple observations for that subject, then you have a time series variable. An example of this would be studying democracy in the United States between 2001 and 2017. There would only be one subject in the United States with multiple observations between 2001 and 2017. If your variable applies to multiple subjects and you only have one observation per subject, then you have a cross-sectional variable. An example of this would be studying democracy in all countries throughout the world in 2017. There would be multiple subjects, all countries in the world, with one observation, 2017. If your variable applies to multiple subjects with multiple observations per subject, then you have a cross-sectional time series variable. An example of this would be studying democracy in all countries throughout the world between 2001 and 2017. There would be multiple subjects, all the countries in the world, with multiple observations between 2001 and 2017. Going back to our democracy variable, our unit of analysis was countries throughout the world in 2017. In our variable, we would have observations from multiple subjects, all countries in the world, with one observation in 2017. That would make our variable a cross-sectional variable. After we collect our data, we have to review our variable to make sure we are measuring what we want to measure. A variable is valid if it measures the concept it intends to measure. It is invalid if it does not measure the concept it intends to measure. It matters if our variables are valid measures of our concepts. If a variable does not measure what we want it to, then we may draw false conclusions in our analyses. In addition, since different variables measure the same concepts, for example, there are several different measures of democracy, we are able to compare the validity of these measurements in order to be able to choose the most appropriate one to use. There are several reasons why a variable may be invalid. For example, systematic measurement error occurs when we create an operational definition that consistently mismeasures our concept for a specific reason. One reason could possibly be that the variable measures more than we think it measures. For example, going back to our democracy variable, we said that we would use data from the CIA World Factbook to determine if countries had free and fair elections and leaders were held accountable for their actions. If the CIA World Factbook is an unbiased source of information of countries throughout the world, the information it gives us would allow us to collect a valid measure of democracy throughout the world. However, if the CIA World Factbook is biased in such a way that it is less likely to publish unflattering information of U.S. allies, then our variable may lead us to code some non-democratic countries that are U.S. allies as democracies. Then our variable would not only be measuring democracy, it would also be capturing U.S. government bias of countries throughout the world, a characteristic we did not intend to measure. U.S. bias is causing systematic measurement error in our measure. If that happens, then our variable would be invalid. The solution to this problem is to find an unbiased source of information to code our variable. The Hawthorne effect also leads to systematic measurement error. The Hawthorne effect occurs when you're collecting data from individuals and those individuals behave differently because they are being observed. So, for example, we know that when survey researchers ask respondent questions about race-related issues, the race of the survey researcher and the respondent matter. African American survey respondents are more likely to say they face discrimination when an African American survey researcher asks them questions about discrimination versus when a white researcher asks them questions about discrimination. Hence, the survey questions are not only capturing African American attitudes on discrimination, the intended characteristic, they are also capturing social pressure and an unintended characteristic. The solution to this is to have survey respondents fill out a paper survey that is confidential so they don't feel pressured to answer a certain way based on the characteristics of the survey researcher. The way we code our variable could also lead to systematic measurement error. Recall that we coded non-democracies as 0 and democracies as 1. It is easy to classify countries that are purely democracies or purely non-democracies, but there are several countries throughout the world that are not clearly democratic or non-democratic. Russia is a perfect example. There are elections in Russia, but leaders are rarely held accountable for their actions. Should Russia be classified as democracy or not? It is a tough question. In order to overcome this problem, we should probably go back to our operational definition and refine it. We could add another category to the definition. Democracies could be coded as 1, mixed systems could be coded as 0, and non-democracies would be coded as -1. Another threat to the validity is the ecological fallacy. An ecological fallacy occurs when you collect aggregate level data and apply it to individual level behavior. An egregious example of the ecological fallacy would be assuming that since a state voted for a Republican presidential candidate, all voters in that state are Republican. That is most likely not true, since it is possible that a large minority of voters in the state could have voted for the Democratic candidate, but the Democrat lost. The solution to this problem is to conduct a survey to gauge how many people in a state voted for Democrats versus Republicans. There are several different ways we can evaluate whether a variable is valid. The two I am going to talk about in this lecture are face validity and construct validity. Generally speaking, the face validity test is when researchers examine how a variable is measured and determine whether the variable is a valid measure of a concept. Often experts will look for the potential for systematic measurement error in a variable based on how it is measured. If there is any potential for systematic measurement error, they may conclude the variable does not pass the face validity test. For example, we could look at our democracy variable and think deeply about whether there may be reasons why the variable might miscode some cases. We already did this when we discussed threats to validity in the previous slides. For example, we talked about how it could be possible that the CIA World Factbook was biased and could lead us to miscode some non-democratic U.S. allies as democracies. If this is the case, then the democracy variable would fail the face validity test and would be considered an invalid measure of democracy. Next, there is also contract validity. The contract validity test helps us determine if a variable is a valid measure of a concept. In a contract validity test, we determine whether our variable is correlated or related to similar variables it should be related to. We could compare our democracy variable to a human rights variable, as we know democracies are more likely to have good human rights practices than non-democracies are. If we compared our democracy variable to a human rights variable but discovered that the two variables were not correlated, our democracy variable would fail the contract validity test. Not only do we need to evaluate whether our variables are valid, we also have to evaluate whether they are reliable. Reliability is the extent to which a variable consistently measures a concept across all observations. A variable is not reliable if it does not consistently measure subjects or cases the same way when we apply our coding criteria for those cases. Using our democracy variable as an example, the variable would not be reliable if some countries were coded differently by different coders. It would be reliable if all the coders measured the countries the same way. The reliability of a measure matters because if our variable is unreliable, some of our observations will not be measured properly. Therefore, we are less likely to trust the results of our analyses if our data are not coded consistently well. One threat to reliability is when you have multiple coders coding a variable and they sometimes have to make judgment calls about how to code a particular observation. So, for example, one of the coding criteria for the democracy variable was whether a country's electoral rules do not favor one party over the other. This is not an objective criterion, it's subjective. As such, two coders might disagree over whether a country's electoral rules favor one party over the other. If that is the case, one coder may code a country as a democracy and the other might code it as a non-democracy. One coder would clearly be correct, the other would not be. As a result, the democracy variable would be an unreliable measure of democracy because sometimes it measures democracies and non-democracies correctly and sometimes it does not. There are several different ways we can evaluate reliability. One way is the test-retest method. In the test-retest method, we apply the coding criteria from our variable to the same subjects repeatedly to make sure the variable produces the same coding outcome every time. When we have multiple researchers coding our data, we can use an intercoder reliability score to make sure the variable produces the same coding outcome for each subject in our data set, regardless of which coder is coding the data. A simple intercoder reliability score is the percent agreement measure. It is calculated by dividing the total number of cases that coders agree upon divided by the total number of cases overall multiplied by 100. So in this example, coders 1 and 2 agree on the codings for country A, country B, and country D. The percent agreement measure would be 3, the number of cases that the coders agreed upon, divided by 5, the total number of cases, times 100, or 60%. If you do find out that a variable has a very low intercoder reliability score, one solution is to have a principal investigator make the final coding decisions for observations that are coded differently by different coders.